Equip yourself with the right tools, and you'll detect the universe's hum everywhere in the sky. This isn't sound traveling through space's vacuum, it's the hum of gravitational waves. Decades ago, scientists found a similar signal known as the cosmic microwave background. This afterglow from the Big Bang was a monumental discovery, confirming the Big Bang as the foremost theory of our universe's origins. However, this light signal had a major limitation. It appeared nearly 400,000 years after the Big Bang. To explore even earlier, we need a background signal not of light, but of space-time ripples. In 2023, astronomers from the Nanograv collaboration announced a breakthrough. By using an innovative method, they might have detected this very signal. They used exotic stars as a massive gravitational wave detector, capturing the faint hum of space-time itself. This hum could be the echoes of the universe's creation. To know more, stay with us till the end of this video. Gravitational waves stretch and squeeze space-time, changing the time it takes for light to travel through a tunnel. Detectors like LIGO can sense these waves, but only a specific kind, those with high frequencies. These high-frequency waves occur when two massive objects, like black holes, spiral rapidly towards each other, completing hundreds of rotations per second before colliding in a big explosion. However, LIGO can't detect the early stages of these spirals, where objects are orbiting at much greater distances. These distant orbits produce low-frequency gravitational waves with less energy, creating a faint hum rather than a loud bang. Larger black holes add more to this faint hum, with the loudest contributions coming from pairs of supermassive black holes found at galaxy centers. These enormous binaries, billions of times the mass of our Sun, are rare and form only during extraordinary events like galaxy mergers. When galaxies merge, they mostly pass through each other due to vast interstellar space. Few stars or planets actually collide. Instead, the star's gravitational pull merges them into one galaxy, and the supermassive black holes at their centers form binaries that keep orbiting each other long after the merger. These post-merger binaries are what we would hear most clearly in the ultra-low frequency range, specifically around nanohertz. Just as our ears can't hear very low sounds, LIGO can't detect this cosmic noise. If we could, it would reveal secrets about galaxy mergers and black holes. But there's more. The gravitational wave background offers a peek into the universe's earliest moments. Let's quickly review the cosmic microwave background. This is the oldest light we can see because, for the first 400,000 years, the universe was opaque to light. What does opaque mean here? Initially, the universe was too hot for neutral atoms to exist. Electrons and protons had too much energy to stick together, filling the universe with plasma, a state of matter like the one inside stars. In this plasma, light couldn't travel freely because it kept hitting the charged particles, getting absorbed and re-emitted constantly. As the universe expanded and cooled, protons and electrons could finally form neutral hydrogen and helium atoms, making the universe transparent. Light could then travel freely. This light was stretched as the universe expanded, turning into microwave light, which we now see as the cosmic microwave background, the oldest light in the universe. But unlike light, gravitational waves are ripples in space-time itself, and plasma doesn't block them. From the very start of the Big Bang, gravitational waves have traveled freely through the universe. They pass through the plasma barrier, offering a glimpse into the universe's earliest moments. As these ancient waves have journeyed through time, their high frequencies have stretched out due to the expansion of space-time. This stretching redshifts them into extremely low frequencies, similar to those produced by merging black holes. These varied sources create a mix of low-frequency gravitational waves known as the stochastic gravitational wave background. How do astronomers unlock this treasure trove of information about black holes and the Big Bang? Can we upgrade LIGO to detect the Earth's movements in these massive gravitational waves? LIGO operates by sending two beams of light down perpendicular tunnels. Mirrors reflect these beams back to their starting point, where they are compared. If space-time warps in one direction, the comparison helps measure the distortion. However, detecting these low-frequency gravitational waves with a new LIGO would require much longer tunnel arms than we can currently build on Earth. The frequency of a wave is inversely related to its wavelength, meaning ultra-low frequency waves have very long wavelengths. To observe the effects of these waves, we need to measure changes over a much greater distance. Nanograv pioneers the exploration of gravitational waves through a sophisticated method employing pulsar timing arrays. These arrays capitalize on the inherent stability of pulsars, dense remnants of supernova explosions that emit beams of light akin to cosmic lighthouses. By meticulously monitoring these pulsar signals, Nanograv constructs a virtual interferometer spanning thousands of light years. This ingenious setup transforms the cosmos into a vast gravitational wave observatory, using Earth as a distant receiver. Central to Nanograv's approach is the strategic placement of 68 millisecond pulsars across the sky. These pulsars, distinguished by their rapid rotation rates, serve as precise timekeepers dispersed throughout space. The key lies in detecting minute changes in the arrival times of pulsar pulses, which can indicate the passage of gravitational waves. Variations due to Earth's motion and interstellar disturbances are meticulously accounted for through statistical analyses, ensuring that genuine gravitational wave signatures are distinguished from random noise. To detect gravitational waves, Nanograv focuses on pairs of pulsars located at opposite ends of hypothetical arms extending across space. When a gravitational wave passes through, it distorts the fabric of space-time, causing a characteristic stretching and compressing effect along different axes. This effect subtly alters the arrival times of pulses from the pulsars, correlating their signals in a pattern known as the Hellings and Downs curve. This statistical correlation, when observed over time, provides compelling evidence for the existence of a gravitational wave background. On June 28, 2023, after over 15 years of meticulous observation and analysis, Nanograv announced significant findings. Their data exhibited the hallmark signature of gravitational waves, showing correlations between pulsar pairs consistent with theoretical predictions. Despite the inherent uncertainties, statistical significance at the 3 sigma level, indicating a 1 in 1,000 chance of a fluke, underscores the robustness of their findings. As Nanograv continues to refine their techniques and gather more data, the quest to officially confirm the gravitational wave background promises profound insights into the fundamental nature of the universe. What secrets does the gravitational wave background reveal? While we can't yet pinpoint the exact sources of this cosmic noise, these methods will soon let us listen in on specific supermassive black hole binaries and decode what these signals tell us about the universe's beginnings. Until then, astronomers will continue using their galaxy-sized detector to track our movements in the turbulent sea of spacetime. Have you heard of Nanograv before? What mysteries do you think gravitational waves might uncover? Let us know in the comments section down below. And if you found our video informative, then do like it and share with your fellow space enthusiasts. Subscribe to our channel for more content like this on space science.